All right, here it is. Results of the exam. Look at this, a perfect curve. From left to right, as widely spread as you can possibly imagine. That's exactly what you want, so one can separate individuals and can assign proper grades. So the best score, I think, was 242 or somewhere up here, and the mean was 152, 61 percentile. That's really excellent. So you guys learned something, and the trick now is not to rest on your laurels, but keep on adding new material. Standard deviation, whatever that means, I have no idea, 44, because it's meaningless, but you guys like that to mean something. So those of you who are up here, don't relax. Just keep your schedule. Seems like it's working for you. The essence is it's possible to do work every day, but not excessively. An hour a day, maybe less, whatever suits you. But keep on doing it every day because that's the way you assimilate the stuff the best. Anybody in the middle that you're basically in the pack, so to speak, it's too early to make judgments, so don't be disappointed. It's like the Tour de France, so the pack, the difference between number 6 and number 96 is nothing. They're all coming in a pack. And some of the differences from here to here, you notice that's 130 to 170, be 40 points, that's one question in the final exam, for example. Okay? So if you're down at the lower end here, it's a wake-up call. You have to ask yourself what went wrong. Either you didn't study enough or you tried to cram. Cramming is a complete disaster. In the exam, all the molecules start fighting each other, and they start dissolving your brain, and even stuff you know suddenly is not available. Okay? So that's really bad. That's why I'm saying it's like a language. I mentioned this before. Starting a language, every day you do a little bit of practice, and slowly you get into a rhythm. So you got to catch up here and definitely speed up increase the intensity of your work on this material. Okay, so we started to talk about carbonyl reactions, and today we're going to go heavily into new vocabulary, 8 or 9 new words, so to speak. We mentioned that the carbonyl function is polarized, and so it's Coulomb's law, and all reactions really follow it. So in that sense, you can generalize it, and even without knowing a reaction, you can predict how things are going to add, because nucleophiles will add to the carbon, and electrophiles to the oxygen. And as we said, all the electrophiles we're going to deal with are only one, namely proton. Okay, so it's addition here, and then you come out with an OH. And we did this first with hydration, where water added to the or hydroxide added to the carbonyl carbon, and then the oxygen was protonated, and that gave us these geminal diols or hydrates of aldehydes and ketones, and they're in equilibrium with the starting material, and we could shift the equilibrium depending on the structure, or adding excess of water, you can control to some extent where the equilibrium lies. And we then moved on. Well, we discussed the mechanism. These things occur always by 2 possible mechanisms. One is acid. Acid is typically used when you need to increase the electrophilicity of the carbonyl carbon, so the proton hits here, and that makes that guy even more delta plus, and that speeds up nucleophilic attack. This is particularly good when you have a nucleophile that's a lousy nucleophile, like water. Alternatively, with base or without acid, assuming that the nucleophile is sufficiently basic and nucleophilic itself, you get direct attack at that carbon. So we did this in the basic hydration, where instead of water attacking, which needed protonation here, then water attack, we used hydroxide. Hydroxide was a good enough nucleophile that attacked first, and then protonation occurred later. These two will repeat. I mean, we'll see those, I would say 50 times from now, okay, on various systems, but it's always the same. It's either protonation first, nucleophile adds later, or nucleophile adds first, and the proton adds later. And so the trick is only to recognize a nucleophile as a nucleophile, which you can often guess by just looking at the product. So then, from the hydrates, we moved on to alcohols, where one of these hydrogens was replaced by an alkyl, and these we call hemiacetals, and they are governed by the same equilibria as hydration. And then there was a special process where with acid, and this only works with acid, we could remove the OH by protonation and water leaving to make an alkoxycarbocation. And that can then be replaced by another alkoxy group, so that instead of 2 hydroxys, we have 2 alkoxys. And those are the equilibrium situation, and thermodynamic stability of those is such that they can be isolated. So you can drive all these equilibria towards the dialkoxy species, which we call acetals. And the usefulness of that was in protecting group strategies, you can turn a carbonyl into an acetal, meaning the reactive CO function turns into an unreactive ether function. And you can release the carbonyl from the acetals by hydrolysis. And so we had a mechanism that we went through last time. The salient features were 2 sequences. The first one is just hemiacetal formation, where with acid you protonate first, alcohol adds later, and you get the hemiacetal. And then the trick was that with acid you can remove this OH and replace it by OR, by a simple relay. Looks more complicated than it is, and it's just because it goes stepwise. There's arrow pushing and stuff. But it's basically protonating this to turn this into a leaving group, and the carbocation is then trapped by an external alcohol. And that gives you the acetal. So instead of going through this again, there's a movie where we can see it again. And so here's the aldehyde function. It gets protonated. That activates the carbonyl, so you have a strong delta plus here. And so then the alcohol, and so then that's important, right? So we have resonance forms. This is to drive home the fact that a protonated carbonyl is the same as a hydroxycarbocation. And I've said this at least 10 times now. Alcohol then adds, and you remove the proton, so that's the hemiacetal. And now we're going to exchange OH with OR. So here comes the proton. Of course, it's solvated, presumably by the alcohol, and it gets delivered to the OH, and then this leaves, and here we have now an alkoxycarbocation that is stabilized by resonance through this electron pair to give you an octet. Then the alcohol traps this species and deprotonation, and then you're done. And here's your protected diether type acetal protected carbonyl compound. And so in order to hydrolyze it, we go back through exactly the same mechanism, only backwards. That's why in the mechanism slides we show everything in equilibrium. Okay, everything is in equilibrium error. So if you want to, if I ask you to write the mechanism of hydrolysis of an acetal back to the carbonyl, you start at bottom right and then work your way in the opposite direction. And this is what's called the principle of microscopic reversibility. In an equilibrium scenario, if you push into one direction, you have a mechanism going from left to right. If you start from right and push it to the left by using excess water, in this case an acid, it's the microscopic reverse of the forward steps that connects products back with your starting material. So you can't deviate from that. That's it violates thermodynamic laws. Okay, so as I said earlier, whenever there is an intermolecular reaction, there is also an intramolecular variant, at least in most cases. So one can look at the intramolecular acetal formation, for example, starting with a hydroxy carbonyl, in this case a hydroxyaldehyde. And this, as we already, we've seen this guy before, with a little bit of acid, it's in equilibrium with the cyclic hemiacetal. So if you have acid there in excess, external alcohol now, the hydroxy of the acetal is replaced by methoxy by exactly the same mechanism that we just saw a minute ago. So I'm mentioning the intramolecular variants always separately because in human minds, this is conceptually more difficult. To turn something acyclic into cyclic and the opposite, turning something cyclic into acyclic, it takes a separate step in your mind to really follow this, okay? Even though one could argue it shouldn't, but this is the way we work. And so you can see how this molecule cyclizes in and you make a cyclic acetal. In this particular scenario, basically you're locking the ring as the acetal because you're now blocking the hydroxy that's in ready equilibrium with the starting hydroxy butanol. So to give you a reminder of the mechanism of acetal formation, let's do this on the board, how this works. So here we have the hydroxy butanol, and we're exposing it to acid and methanol, so H plus and methanol. Really, this H plus is presumably sitting on this OH because we're using methanol in large excess, but this H plus could be sitting on this oxygen or on this oxygen. And indeed, this is the proton jumps around, okay? And indeed, this relates to an issue that often comes up. Some of you have already asked me this when I get up in office hours and somebody asks me, how does this work? And I get up and show the mechanism from starting material to product. And then somewhere in the middle, they say, well, why doesn't this go there? Or why doesn't the proton attack here? And the answer is, it does. Everything that's possible occurs. Only all of these reactions are side reactions or dead-end reactions. They don't go anywhere. And so when you're in doubt, when you're not clear, when you say, why doesn't it go here? Do it. Okay? Let the proton go somewhere else, or let the carbon migrate in opposite direction, or let the hydride shift in the opposite way, and see what you get. And you very quickly will realize that this doesn't go anywhere, or go to something completely impossible, a structure that's not feasible, pentavalent carbon, or highly strained, or something like that. So you explore this avenue, and it just comes right back. Since everything is reversible, all these equilibria occur. Okay? So here, in order to get to product, I write this arrow. But indeed, this guy is, can be the source of the electron pair for proton, and also this. But those two options don't go anywhere. Okay? Attack here gives you a species. And I'm now rearranging the molecule to set myself up to the next step, where you have the protonated carbonyl. That activates this carbon with respect to now intramolecular trapping by the hydroxy. Since it's intramolecular, it's particularly fast. Entropically favored, you can also call the entropy effect a proximity effect, if you like that better. And so it attacks here to give you the next intermediate, which is already the cyclic structure. And so then you're deprotonating, and again, that proton is being plugged off by any electron pair that's floating around, presumably methanol in most cases, because it's there in excess. And then we go on, proton comes back in, and now in order to get to product, I'm protonating here. But again, this proton could also hit here, which actually leads you back to where you came from, or it could protonate some of the stuff, anywhere. But this is the one, this is the protonation that gets you to where you want to go. And so now we have the protonated hydroxy, which turns OH into H2O, which is a good leaving group. And so the leaving group leaves, water pops off, and now we have this intermediate, this carbocation, which you notice is a carbocation that's stabilized. There's another resonance form where you use the electron pair to give you the octet. The octet is actually the dominant form, so most of the charge is on oxygen, but attacking oxygen when nucleophile doesn't work because oxygen wants to be divalent, so attack here is favored. So even though there's less of a positive charge here than there is on oxygen because of the octet resonance form, that's the productive step. And here's where now methanol comes in as a reagent. And now we're losing the final proton, and you have the acetal, the cyclic acetal. Now, in this protecting group strategy, you notice we are protecting the carbonyl function. That was our initial goal, our initial realization. But of course, the protection is actually mutual. When you protect a carbonyl with an alcohol, they're actually mutually protecting each other. The carbonyl is protected as an ether, which is relatively unreactive, and the alcohol is also protected as an ether, relatively unreactive. And that can be used in a variety of ways, as we shall see. Now, for using acetals for protection, you can just use a cheap alcohol like methanol. And if there is a need to protect a particular species, you can do this with methanol. But remember that when you do this, you are turning 3 molecules into 2, which is entropically not that great, but it's possible. A better scenario is to, instead of using 2 molecules of an alcohol, use a diol, where both hydroxy functions that you're going to use for the acetal formation are in the same molecule, because you're starting with already a much more ordered scenario. Only 2 molecules turn into 2. The other molecule is water that's formed here. And so entropically, you are better off, or less badly off, It's entropically better. And since these equilibria hover around 1 in most of these cases, any little extra pushes the equilibria to the right. Moreover, the resulting products are also more stable. So the classic or the most popular form of protecting an aldehyde or ketone is to use this guy, ethane dithiol, or for short, ethylene glycol. This is the stuff that's in antifreeze. Okay? That's in your coolant in your car. This molecule, so it's dirt cheap, mass produced, and this molecule with an aldehyde in the presence of acid will now make a cyclic acetal. Okay? As an aside, remember this carbon is tetrahedral, so even though this is written sort of in a flat structure, if you do the zigzag in the plane, then one of these oxygens comes towards you, the other one goes to the back of the board. It's arranged in a perpendicular arrangement. So this acetal, in this case 73%, protects the carbonyl function, and you can do whatever chemistry you wanted to do it in a larger structure on another part of the molecule. And if you want to deprotect, you just treat this with dilute aqueous acid, a lot of extra water, and that shifts the equilibrium back to the left. So in this case, the focus was on protecting the carbonyl function, but coming back to the mutual protection, if you wanted to protect the two alcohols, that wouldn't be necessary normally, but the two alcohols of ethane diol, they would also be protected in this form. Of course, this is a rather useless example, so let me give you examples where this is really necessary. So here's an example where we want to turn this molecule into that. And if you look at this retrosynthetically, notice that this portion here, the 5-membered ring ketone and the extra carbon, is already in starting material, but we're adding a new bond and add 2 more carbons here, okay? And so retrosynthetically, we have to cleave here. And since this is an alcohol, this is typical alcohol synthesis, we know this from chapter 8, this requires that we make a Grignard out of a bromide like this, and then treat it with acetaldehyde, okay? And that will give you this extended side chain. But we can't make a Grignard of a carbonyl compound, because Grignards react with carbonyl compounds. So it will be a complete mess, actually. As soon as one atom of magnesium inserts here, it will find another molecule of this and give the alcohol and so on. And you won't be able to do the Grignard with the aldehyde as you want it. So what we need is to get rid of this carbonyl function by protection. And so we do this with ethylene glycol. That turns this into the cyclic acetal. Then we do the Grignard formation here. This is now an ether. Grignards love ethers. In fact, Grignard formation is typically done in diethyl ether or tetrahydrofuran, the cyclic ether. And then you add the aldehyde, and then in one final step, you actually both protonate the alkoxide that's formed from the Grignard addition to the aldehyde. So this initially is formed as O- as the alkoxide salt, but also you deprotect the acetal function, you hydrolyze the acetal function to give you this. So back to the mutual protection, now we can also protect the diol. In this case, the diol was cheap, and this was the expensive piece. But imagine that you had an expensive diol. This is something that will come up especially in the sugar chapter. Carbohydrates are polyhydroxy systems where you need protection of diols. And so let's assume you wanted to convert this into that. Okay? That means that looking at this piece here, the cyclopentane diol is the same, but we've added 2 carbons. And this can be done by turning this into a Grignard and treating it with oxocyclopropane, which does the ring opening and then introduces a hydroxyethyl function. It's a useful transformation to keep in mind retrosynthetically. Hydroxyethyl is masked oxocyclopropane. So you can't make a Grignard of an alcohol either, because the alcohols are acidic. And Grignards, as well as alkyl lithiums, are extremely hygroscopic, water or proton sensitive. They immediately get protonated because they're such strong bases. So you need to protect that. So now you use a cheap ketone. Among the cheapest ketones is acetone. So you make the acetone acetal of this diol, so mix that with acetone, use excess of that with a little bit of acid, and out comes the cyclic acetal. And now you can do your Grignard and add oxocyclopropane, that anion attacks and ring opens this, and then you protonate the alkoxide that's formed here, and at the same time hydrolyze the acetal back to the diol. Now you have a triol. Okay? So that's the way it's done. So now your retrosynthesis has a little twist. You can simplify it in terms of saying, okay, I know this and that, I know how to add this. This can be done best by a Grignard step here. Okay? So you can retrosynthetically cleave here, but be cognizant of the fact that you need to protect the functions as the cyclic acetal. So you don't need to write that retrosynthetically. The protection steps, it's, you will get good enough to realize, okay, I need to also protect this, but this is the strategy. Disconnect here, a Grignard plus oxocyclopropane will introduce this chain. And similarly up here. Okay, so in chapter 9, when we discussed alcohols, we moved from oxygen to sulfur briefly in a subsection of chapter 9 to thiols, because thiols are sulfur analogs of normal alcohols. And so a lot of the reactions of thiols are very similar to those of normal alcohols. There are quantitative differences because sulfur is bigger, it's more polarizable, etc. But otherwise, it does very similar things. And the same thing is true when we switch from ethylene glycol to the sulfur analog of ethylene glycol, ethane thiol, dithiol. And that guy will turn aldehydes and ketones into the corresponding sulfur analogs of the cyclic acetals, namely so-called cyclic thioacetals. And the reason that this is important is because these are even more stable than the normal oxygen-based acetals. So this is often the case when you need better stability. And we'll see species like this later also in the heterocycle chapter. So this is one way to make these thioacetals. Notice the conditions are very similar, except that instead of using protic acid, this doesn't work so well, people use Lewis acid. And for ethane dithiol, you use zinc chloride. So you need zinc chloride in order to push this from left to right. So there's a new piece of vocabulary. Instead of proton, you use zinc chloride. And then the